So recall, whenever we say log base b of x, whenever we say something like this, what is it that we are supposed to ask ourselves? So what does this mean? So this equals to what?
N.
So what does this equal to in words?
B to what power equals x?
Very good. So this is a number. What number is this? The power required to raise b to obtain x. Okay? So this right here is the power of b, or actually to say, this is the value that b must be raised to get x. Okay, so in other words, and let me write it like this now. If we have log base b of x equals to y, what does this mean? This is equivalent to what?
B to the y.
If we do b to the y, we obtain x. Okay, so whenever you write this log business, this is just an exponent. What exponent? The one that you need to raise b to obtain this value. Okay, so if log base b of x equals y, that means that if you do b to the y, you're gonna obtain x. Okay, this right here, you can do most of the things that have to do with logarithms. You can do it with this little box that's in here. Okay, so I'm gonna box this. By the way, so I guess a little example, as usual. Let's keep the same one because that one is very nice and easy to remember. So if we have log base 2 of 8, so by the way, this is called the base. We define it as a function, then we give names. But this is called the base, and this is called the argument of the logarithm. Okay? So log base 2 of 8, what is that equal to? It's equal to 3, because if you do 2 to the 3, you get 8. Is that okay? That's just a fancy way of talking about this guy, okay? This exponent right here. That's all it is. Now, in here, there are some little names that we can say. For example, notice that these two expressions, they are equivalent, okay? So this line right here means exactly the same as this one over here. Now, we say this is the logarithmic form of the expression, while this one is called an exponential form, okay? It's the same idea, but written in different forms. So we call this logarithmic form, and this one we call it exponential form. And then, a little exercise is, if I give you one form, then you write in another. I give you logarithmic form, write it in exponential form. I give you exponential form, write it in logarithmic form. So let's do that. So exponential form. Okay, so let's do an example. So write in logarithmic form. So notice the pattern, okay? Whether you go back and forth, and notice that the base of the log and the base of the exponent is always the same, okay? In the case when you go from exponential to logarithm, the base of the exponent is the base of your log, and then the exponent itself is what the entire log equals to. Okay, remember, log is just exponent. So that means that whatever is in here, it has to go in this piece, in this pattern. Okay, so it's very easy to hopefully make that connection. So write logarithmic form, and then let's see, let's do number 1. Let's do 2 to the 3 equals 8. And let's do 8 to the 0 equals 1. 3 to a negative 3 equals 1 over 27. And 5 to the x equals 125. Okay, so who can tell me what's the logarithmic form of the first one? We just wrote down, yes?
Log base 2 of 8 is equal to 3.
Log base 2 of 8 is equal to 3. Good. Any questions on this? Again, the base here is the base here. The entire, this exponent over here, which is 3, is going to be equal to the entire log, and then, of course, this guy, which is the left you put it in here. Okay? And you can always verify. I guess going from the log form to the exponential form is easy. You just follow this pattern. This number raised to this power has to give you this. Okay? 2 to the 3 equals 8. Alright? Okay. How about B? Who can tell me? Yes.
Log base 8 of 1 equals 0.
Log base A of 1 equals to 0. Very good. And then, you can visually observe that 8 to the 0 equals 1. Coincides with this. Okay? Alright, good. Who can tell me the next one? How about the next one?
Log base 3 of 1 over 27.
Of 1 over 27 equals -3. Good. Do you understand how to do this? Yes or no? Okay, so how about the last one? So, how about the last one? Yes.
Log base 5 of 1 and 5 equals x.
Equals x. Very good. Okay, questions in writing an exponential form in logarithmic form? No? Okay, good.
I
Yes.
just have one question. So
Uh-huh.
for D,
Uh-huh.
the solution there would be x is equal to 3. So
Uh-huh.
if there's a question like that on the test, should we write x or 3?
Well, it depends. What's the question is asking here?
It's asking to convert to logarithmic form.
So that's what you need to write. If you write 3, that's not logarithmic form. And now, if the question says solve the equation, that's a different story. Now, I want to know what x equals to. It's true x equals this, but now there's a number. Typically you don't say this. Oh, x equals 2 plus 3. You don't give an answer like this. You tell me x is 5.
Yes.
So if I ask you to solve this equation, then you can do this, but then you need to go ahead and evaluate this. Okay? The point is, there's another way that we'll solve this instead of doing that. But anyway, you can do that, and then you can compute it if you like. Okay? Good. All right, so now let's do it backwards. I give you the log, and then you write it exponential. That one is typically easier, okay? Because again, there is this little circular part that you do. This number raised to this power has to give you this, okay? So it's easier to go back. All right, so, but let's practice it just in case. So write in exponential form. And then you do log base 10 of 1,000 is equal to 3. And let's do log base 25 of 5 is equal to 1/2. Log base 4 of x equals to 200. And then log base e of x is equal to y. Okay, so how about the first one? What is it? Yes?
10 cubed equals 1,000.
10 to the 3 is equal to 1,000. Good. All right, the next one. Let's see here in the front row. What's B? Tell me. How do you write this exponent? Very good. Okay, back row. How do you write C?
What is the 200 equals x?
Very good. And then, whoever, part D. How do you write this?
What's the number next to 1? The 2.
E. We talked about this number last time. Remember, this is 2 point something. It's a number between 2 and 3. 2.71, etc. It's an irrational number. Like saying pi. Yes?
E to the y equals x.
E to the y equals x. Good. So, are you okay going back and forth in this? All right, perfect. Again, we're going to need this because when you want to solve equations, you have to be able to do this kind of stuff. Okay? So, I'm going to come back to that. Okay, so before I continue, and actually we made this a formal function, let me just introduce a notation. There are two logarithms here that are special. So let's see. Actually, let me talk about, okay, let me talk about the function and then I will talk about the logarithm. I'm talking about a and b. Okay. So when the base is a number 10 and when the base is a number e, we have a special notation for this. We call this the common logarithm, and then what we do is we avoid this base. So if you write log without the 10, it's implicit that the base is 10. If you look at your calculator, you're going to see a key that says log. That means log base 10. Okay? And then also we have a special notation for this one. When the base is e, instead of writing like this, it's called the natural logarithm, and then we write ln. You need to understand that when you write ln, we mean log base e. It's exactly the same thing. Okay? All right, I will write that down, but first let's define the function. So definition. Now you understand this operation, we can make this a function. So logarithmic function. And actually, before I do that, let me okay. Let's do it this way. Definition, logarithmic function. All right, so let b be a positive number, different than 1. And okay, I'm gonna say why is it that we're saying this. So let b be positive, different than 1, and x be a positive number. Then the expression f of x equals log base b of x is called logarithmic function with base b. Okay? And I mean, this is exactly what we have been doing. It's just that now this operation that we typically do, when you compute something like this, when you're asking is b to what power is equal to x, now we can turn this into a function. Okay? Just give me an input here, then the input goes in here, and then you calculate the output using this operation. All right? Let's talk a little bit about these restrictions. Let's see, who can tell me why do I need to require x to be positive for this to make sense? Yes.
Because with logarithms, you're finding to what power something is, the power to which something is equal, and you can't have a square root of a negative number. That is real. I don't know if I'm wording it correctly.
Wait, I don't understand.
Because you're dealing with exponents, and you can't have the square root of a negative number.
Okay. Okay. So okay, why are you talking about square root? And
I don't think I really.
okay, so I mean it's pretty simple to justify this. Remember, we talked about exponential functions before. What did we say about exponential function? What's the range of an exponential function?
0 to infinity.
From 0 to infinity. When you do exponential, you always get something positive, right? Now, x is supposed to be b to some power, right? So x is the result of an exponential. It's in the range of an exponential function. Do you understand this? Because it's the result of doing b to the something. And when you do a number raised to another power, the answer is always positive, by definition. So that's why we need, for this to make sense, this better be positive. Does that make sense? You cannot do log of something negative, because there's no power that will give you something negative. I understand that that's probably what you want to say, but you just put your words together nicely. Okay, good. So now we understand why we're saying that x has to be positive. Next, why are we requiring this? Okay, so the reason why we require this, first of all, because otherwise it wouldn't be interesting. Like, if we make this a 0, then what would be the only thing that we are allowed to write here? A 0, okay? And we don't even want to do that, right? So 0 to what power it equals whatever. Well, 0 to anything is just 0, except 0 to a 0, which is undefined. Okay? But other than that, then it's not interesting really, so that's why we avoid 0 here. Also, why do we avoid 1? For the same reason, because 1 to what power equals x? Well, 1 to whatever is just 1. So, the only thing then that you can put here is a 1. And then it's not an interesting function at all. Okay? So same type of restriction that we have for exponentials, we have it here. Remember, the base of an exponential has to be positive and different than 1. Same thing for logarithm. The base must be positive and different than 1. You okay with this? So with this definition in particular, you can see that x represents the domain, right? So we can say here the domain of the logarithmic function is from 0 to infinity, right? Because of that nature. Now we're going to say more properties about it. So we understand this operation. Now we define this as a function. Let us just remark something. So note. So let's see. Let's consider the function f of x equals log base b of x. And let's consider g of x be the function b to the x. Okay? Let's look at these two functions. Let's do little colors. So this is my logarithmic function, and now let's take a look at the exponential function. And what I want to do is I want to do the composition. Okay? So for example, let's do, we're big guys, so we can do this in general. There's no need to do a concrete example. So let's say that this is the function f, right? This is the logarithmic function. And here we have the function g. Okay? All right. So let's say that we have an input. So x comes in here as an input, right? What comes out? Who can tell me? What's the output of this? Remember, composition means you do one function after the other, right? You first do the first one, and then, by the way, this picture represents what? What does this picture represents? We're about to write here. What is it? I just said this is composition. What composition is this? We talked about this last time. What composition is this? This is g of f. Remember, the one that goes inside is the first one that you do. When an input comes in, what's the first function that we apply? According to this picture? F, right? So this is g composed with f. Let me bring this down a little bit. So this right here represents the composition g composed with f, okay? So this is g composed with f. That's g of f of x. Okay, let's do it. So if x comes in, then f is the first one that acts on it, and then because f is the logarithmic function, what you get here is log base b of x, right? Okay, now who can tell me? If this goes into the blue function, remember, this is the exponential. The job of this function is to do whatever comes in, it does b to the power, right? What would be the result?
B raised to the log base of x.
But tell me what's the result? Why?
Because the inverse.
Why? That's what we're trying to figure out. So. Just think about it. What is this? What is this? Who can tell me in words what is this?
It's B raised to the power of x.
Okay, that's a question. Now tell me what is this as a statement?
Log base b of x.
Yeah, okay, but what is this? Yes.
Logarithmic one?
Yes. But what is this? We just wrote the sentence at the top of the, I guess, the screen today. That question that you asked, but now make it a statement. Don't make it a question. Make it a statement. What statement can you write here? You know what statement is, right?
Yeah.
Okay. What statement can you write here? So what is this?
The value
Uh-huh.
that you raised B2 to get x.
Very good. Do you understand this? So this is the power that B needs to be raised to obtain x, right? Now what are we doing here? Right, this is a value. What value? The one that you have to do b to the power to get x. Now what is the blue box doing? What's the function g doing?
You're raising B to
Taking b raised to the power. So what are we supposed to get? X. And just by definition. Here we're not even saying that they are inverse of each other. We're going to use this idea to deduce that they cancel each other. Okay? Do you understand what I'm saying? What this represents is the power that b has to be raised to get x. And what it is doing is raising b to this power, right? That's the job of this function. So, of course, by definition, you're going to get x because it's a power that you need to raise b to obtain x. Does that make sense? So it appears that f and g, that g is canceling f. You see, whatever comes, it appears no, we can see. Whatever comes into f, then it gets cancelled by g. So this means that g is the inverse of f. Now let's see if the other way around happens as well. Do they cancel each other? If that happens, then they are inverse of each other. And then we can translate most of the properties that we already know from the exponential function, then we can translate it to the logarithm, and we get them for free. Particularly, we're going to get for free the graph, the domain, the range, and all of that business. Okay? All right, so this means that g cancels f. How about the other way around? So I want a picture now for f composed with g. In other words, we're going to do g first, and then we do f. Okay? So that's my composition. Now, we first do g, and then we're going to do f. Okay, so again, an input comes in, then it goes into g. What does g does to the input? So remember, the job of g is just to take whatever comes in and do b to the power. That's what this function is doing. Now that goes into the next one. And what is this equal to? When you do log of this, what is this? So what is log base b of b to the x? Right? So what you obtain here is log base b of b to the x. That's what you obtain. So let's think about it. What must this be equal to? Why?
Because it's a base of it's log to the base of b to the
Say that again.
that's like log of b to b to the function.
Yeah, okay, but you're reading what's on the screen. I'm asking you why is this x?
When you're doing log, it's not just like so going into the x, like observe the exponent.
That's what we're trying to figure out. I mean, you cannot use what we haven't defined yet, right? I mean, how do you know that? Let's see, why are they opposite to each other? You know, so that's what we're trying to get. Yes.
That's equal to x because what power is do you raise b to in order to get b to the x?
Very good, right? It's like a tautological statement. Like here we're saying this is a value. What value? The power that b needs to be raised to get b to the x. It's x, right? B to the x equals b to the x. Do you understand this? Okay. I mean, do you understand why I don't want you to say the inverse? That's what we're trying to explain, right? Okay. You know, it's like, what is the meaning of meaning? You know, if you add that question is strange. Asking for the definition of something that you are using in the question. So then you start getting, so you have to like rephrase it and say it in other words without using the word meaning. If you want to define meaning, you cannot use the word meaning in, you know, in what you're trying to do. That's the same thing here. We're trying to justify why they are inverse of each other. So we cannot say, oh, this is x because they cancel each other because they are inverse. No, that's observation that we're making now. Okay? All right, good. So we can see that if you do log and then you do exponential with the same base, it's important. If you change the base, then they don't do each other. Does that make sense? If I put here now that g is, I don't know, 2 to the x, and this was log base 3, 2 and 3 have nothing to do with each other, they're not going to cancel. Okay? The base has to be the same. So when the base is fixed, is the same, then the exponential cancels the log, and also the other way around. The log cancels the exponential, as you can see. The same thing that comes in, eventually, that's exactly what comes out. So the observation here is that if you do f composed with g, it's equal to x, and also the other way around, g composed with f, that's equal to x. Therefore, by what we defined last time, f and g, so f of x equals log base b of x, and g equals b to the x are inverse of each other. And this right here, this little observation is a theorem. Okay, theorem. The logarithmic function y equals log base b of x is the inverse of the exponential function. Of the exponential function y equals b to the x. Okay? So, in particular, that means that everything that we know about exponentials, then we can deduce a lot of stuff about logarithms. So, let's write that down. So, graph of logarithmic functions. The graph of f of x equals log base b of x. Okay, so just like in the case of the exponential, how many graphs do we have when it comes to exponential functions? How many graphs do we have? Two types of graph. What are they? So when do we get each graph? It depends on what?
Whether x is greater than 1 or whether it's between 0 and 1.
You said x? Or maybe you mean b?
Yes.
It's the base, right? Remember, x is the input, right? So depending on the base, then you have two graphs. So if the base is bigger than 1, you have an increasing function. If the base is between 0 and 1, you have a decreasing function, right? And similarly, each of those graphs are going to give you, they have their logarithmic counterpart. Therefore, for the log, we also have two graphs, okay? Depending on the base. If it's between 0 and 1, you have one shape. If it is bigger than 1, you have another shape. So let's see. Again, b bigger than 1, and then between 0 and 1. So there are two situations. So first, I'm going to write down the exponential, and then we're going to use it to deduce the logarithmic graph. Okay, so remember, the exponential function looked like this. It went through 1, that's the y-intercept, and then this is the shape, the general shape of y equals b to the x. And then, let's say this is 1, so b, let's say somewhere in here. This is the point. I want to say when you plug in 1, you get b. So that's b to the x, and then when you plug in 1, you get b. So this is the point 1 comma b, right? That's how you detect when you have a picture of an exponential function. If you don't have the formula and you want to detect the base, okay, see if the picture tells you what's the output of 1, and that gives you the base. Okay. All right. So that's the exponential function. Now we know this is 1 to 1, so it has an inverse. The inverse is the logarithmic function, and to obtain the graph, what we do is, so what do we do to obtain the graph of the inverse? Good. So you draw the line y equal x. Remember, we saw this last time. You draw the line y equal x, and the reflection, that's the inverse. Okay? So let's draw the line y equal x. It's a 45-degree angle here. Draw it. And then we reflect the picture. So let's see. Remember that the exponential function comes with a horizontal asymptote, right? The x-axis. The line y equals 0. So what happens when you do inverse? What happens to horizontal asymptotes? What do they become? They become vertical asymptotes. So this time, instead of y equals 0, we're going to have x equals 0 to be a vertical asymptote. Okay? This time the y-axis is a vertical asymptote, and now we just reflect the picture. For example, the point 0, 1 becomes, what does this become? 1, comma 0. So a point goes here, and then the point 1, comma b becomes b, comma 1. So let's say that b is somewhere in here because it's bigger than 1, right? So it's like that, and then just reflect that picture. You get something like this. Do you understand this? Now, let me give you a feeling about logarithmic functions, in particular when the base is bigger than 1. This, even though you can see from the picture, is an increasing function, this is actually among the slowest growing function. This is very slow, of course, depending on the base, but it's very, very slow. For example, just to make it more clear, let's assume that the base is 10, okay? Just to make it mind that the base is 10. How long do you need to go, how far along do you need to go on the x-axis to be able to climb one step? So in other words, what I'm telling you is log base 10 of what equals 1. Let's play with this question mark. I'm going to be changing this and then you tell me what goes in here, okay? So let's see. How long do I need to go in the x-axis? So that means how long do I need to go to be able to get 1 as an output, okay? To climb one step on the y-axis. So what you mean here? 10. Everybody understand this? So I need to go 10 units here if I want to go up 1 unit. Now let's say I want to go up to 2. How far along I need to go on the x-axis? 100. You understand this? So to be able for this, this picture really, because to be able to do this, to be here at 2, you have to be already all the way to 100 on the x-axis. You understand this? If you want to go to 6 on the y-axis, how far along do you need to be on the x-axis? What is it? 1 million. Right? It's 10 to the 6, 1 million. So only to climb 6 spots, you have to go 1 million on the x-axis. So this is very, very, very slow. So it's really like if you have base 10, it's gonna look like something that looks almost flat. Okay. So I'm just gonna be drawing this, but I want you to understand that it's not. This is fast. Okay. This is a very small base. This base here is very close to 1. The bigger the base, the slower is the function. Why? Because the bigger the base, the faster is the exponential one. Remember, they are inverse, so they do the opposite thing. If one is fast, the other one has to be very slow. Okay? Okay. So, just to keep that in mind. So that's why, for example, in computer science, you want algorithm. When you design algorithm, when you talk about the speed of algorithm, we want stuff that depends on logarithmic speed. Because, okay, sorry, not the speed. The number of computations that you want to be able to compute something, the number of computations, if it is a logarithmic order, then that means that you're doing very few computations, okay? Because, let's see, because it's very slow. For example, how should I say this? For example, when you have, let's say that you have a list of n objects. If you have something in the order of log base 2 of n, that means that you only really need to do, what is it? A power of 2 that gives me n. That's the amount of computation that you will need to be able to carry out the task. For example, if it's log base 2 of 8, that means that you will only have to do 3 computations to carry out whatever task you can do. Most algorithms, it's very hard to get an algorithm that has this order. For example, there is a structure called binary trees that you can use for searching. Imagine that you have a list of 1 million names. Okay, the names of everybody in Miami-Dade County, for example, and then you want to look for a particular person, and you have that list, and let's say that list is ordered alphabetically. How do you do this? How do you look for my name, Luis Auna? What do you do? You have a list that has millions of names. Yes. How do you do that? Yes.
Like it's a binary form, or
how try to find an efficient way of doing it. For example, the brute force would be start at the beginning of the list and start looking until you find my name, for example. Yes? Now, it's not really efficient. What is my name is the last one. Right? So you're going to go through all those millions names until you find me. So is there a better way? So what will you do? Yes?
so you start from the middle,
Uh-huh.
and then you check the end what it is,
Exactly.
and then you go to the middle of that half.
Yes.
And keep going until you find it.
So how many operations would you do? In general, what's the maximum number of operations that you will do until you find it? For example, imagine that the list has length 8. But whatever we do with 8 is the same thing will apply for 1 million, okay? So imagine that there are 8 names. So 1 through 8. how many operations do we need to do? Maximum. So what is it? You do half, so this is called the binary method, like your classmate. So it's the bisection method. So half of it is, let's say, is 4, right? Okay, so then what do you say? Of course, here we have letters, but you can order things. So half of it is going to be 4, then you compare. Okay, so it's a way to compare names, right? By alphabetical order. So where is it? Is it here or is it here? Oh, it's in here. Okay, then you already caught this in one shot. Now you repeat the process. Half again. What is it? 6. We have done 2 operations. The red lines are the number of operations that we're doing. Okay? And now you repeat the question. Where is it? Is it here or is it here? Ah, it's here. Okay. Half, we found it. If the numbers are 1 through 8. Do you understand this? So was it, of course, if the number was 4, we found it. The number was 6, we found it faster. But what's the maximum amount of numbers that we are going to do it? 3 times. And what is this? Log base 2 of 8. So when you do this half procedure every single time, then the order in which you're doing the operation is a logarithmic order. Okay? So this is very fast. I mean, to search for something like this is very fast. So that's why instead of having a list, because another question is, okay, but if you have things in a list, how do you go to half the list? That's painful. So there's a data structure called binary trees that actually, when you put the things and you do it like this, binary means that each node has 2 childs, and so on and so forth. And then when you're going to put the data, then you start here and you say, okay, where is it that I'm going to put it? Should I go right or left? Well, it depends. If it's bigger than this guy, I go right. If it's less, I go left. And then you start organizing your data that way. And then when you want to search for something, it's very fast to search through a tree. Okay? Because if you have a linear list, to get to the middle sometimes takes time. That's not good. Anyways, logarithm is used a lot in computer science because you want the order of your algorithm to be of logarithmic order. This is rarely, you're rarely able to do this, okay? For searching, yes, but you need to have your list ordered. If it's not ordered, then you cannot do it. Now, the question is, how do you order a list? The brute force method is n squared. It's in the order of n squared. Now, there is a smart method that you can use, and then you can improve this and make it n times log n. Okay? So there's something you can do that you can make it n log n. In computer science, when you see log, it's not base 10, it's base 2. Okay? Because everything is typically half and so on. So you can improve this sorting method and then you can make it n log n. This is better than this because log n is way less than n itself. So this is less than n squared. Okay? But there is no order n. I mean, the thing is that it has to be at least order n because to order something, you need to at least look at everybody. If you don't look at everybody, how can you order the elements? Okay? So, but if you have to look at every single data, then it takes at least n the amount of time, let's say amount of time, number of computations. N number of computations just to look at the data, but then you have to do something with it. You need to sort it. What if the first guy is the one that was in the last spot? Okay? So that's why it's actually impossible to order a list, or there is no algorithm known, as far as I know, of order n to order a list. And this is a very efficient one, but it's n times log n. Anyways, I guess I'm just telling you this because there is real use to this stuff. Okay, it's not just because we want to play with these ideas. Okay, so back here, so that's exponential, and then this is the inverse, and then we got for free the logarithm. This is in the case that the base is greater than 1, and then if the base is between 0 and 1, this is the graph of the exponential function is decreasing. Remember, it's a reflection with respect to the y-axis of this one over here. Okay. So this is 1, and then when you plug in 1, here you have the point 1, comma b. So now again, we do the same thing. We draw a line y equal x. So that's y equal x, and then this final reflection. So let's see, this point goes here, then b comma 1. So this time b is less than 1. So let's say b is somewhere in here. So it's going to go here. And then similarly, the horizontal asymptote, which is y equals 0, now becomes a vertical asymptote, x equals 0, the y-axis. And when we reflect, this bottom part of the exponential is going to go to the top, like so. Okay, so this point here is going to be fixed, and then it goes like this. And then this one that is on top of the line is going to go below. Like. Notice that the point that is on the line y equal x stays there. So this point is fixed. It survives the transition of switching x and y, and then we get this shape. Okay, so this is y equals b to the x when the base is between 0 and 1, and this is log base b of x. Okay, so increasing when b is bigger than 1, decreasing when b is between 0 and 1. So let me now do it without the noise of the exponential function. So graph, so if you have f of x equals log base b of x, then there are two pictures, bigger than 1, between 0 and 1. So the bigger than 1 is this shape, and it goes to 1 here, and then between 0 and 1, x and y is this shape, and it goes to 1. Okay, any questions? You okay with this? So as we did for the exponential, let's write down the properties that each of them, whatever is common to both, I'm going to write it in the middle. What only applies to this one, I write it here in red, and then to the other one, I write it in blue. So let's see, by looking at the picture, I mean, we have it from the definition already, but also looking at the picture now, we can say the domain. What's the domain? From 0 to infinity, and that applies to both. What's the range? For real numbers. In other words, remember, for exponentials, the range was this, from 0 to infinity. You can only get positive numbers with exponential. Now, all of a sudden, with logs, you can get any number in your range. Okay? Any number can be an exponent. That's basically what we're saying here. Any number can be an exponent. Right? You can have positive, negative, fractions, whatever you want as an exponent. That's what we're saying. Remember, logs are exponents. Okay, so domain range. How about x-intercept? What's the x-intercept? 1, 0. What's the y-intercept? There's no y-intercept, none. Do we have asymptote? We have a vertical asymptote. What is it? The line x equals 0. Okay, there's no symmetry. It's 1 to 1, right? So they're both 1 to 1. I think that's the most general thing that we can say about both at the same time. Now, for the first one, when the base is bigger than 1, what's the monotony? Is it increasing or decreasing? The red one. Is it increasing or decreasing? Increasing. Remember, increasing means the graph is going up. And it depends how you read it. Remember, by convention, we always read graphs from left to right. Because if you read it from right to left, it's going down. Right? So in this case, it's going up. So this is an increasing function. Where is it increasing? On its domain. So increasing on its domain, which is 0 to infinity, right? Now, how about the, okay, how about the other one? The blue? Decreasing. Decreasing on its domain. Now, let's talk about the behavior. For example, the end behavior of the red one would be x approaches positive infinity. What can we say about y? So what can we say about y when x approaches positive infinity? It goes to positive infinity. Now, mind you, it's very slow, okay? But it will get there. It's very slow, but it's gonna get there to whatever you want, whatever number you want. You can eventually get it with a logarithm, but it will take you a very big x to get there. Just keep that in mind. Also, there is another value that's special, that's 0. And in this case, from the right, because notice that there is no point talking about 0 from the left. There's no graph to the left of 0, right? What happens when x approaches 0 from the right? It goes to negative infinity. So in this case, the function goes to negative infinity. That's why we have a vertical asymptote, by the way. That's what it means to have a vertical asymptote. It's a special line that when you get close to it, this vertical line, when you get close to it, your value should be either positive or negative. All right, and then how about this one? So when x approaches positive infinity, what can we say about y? It goes to negative infinity. And when x approaches 0 from the right, what can we say about y? It goes to positive infinity. Good. So I guess we have here summarized the problem. Any questions? Do you understand this? Okay. So now we're going to look at logarithmic functions in a more from a more algebraic perspective. Okay. But before we do that, let me formally write down the two special functions that I mentioned before. So the natural logarithm. Okay. So we define log base e of x. We write this as ln of x and call it natural logarithm. Okay. So that means that if you do f of x equals ln of x, so it's a logarithmic function. And what's the graph for this function? Is it the blue or the red graph? Which one is it? Why? Because the base is e and it's greater than 1. Okay? So if you want to see the picture, if you want to visualize the logarithmic function ln, you can have a picture like this in your mind because it has base e, which is bigger than 1. Remember, it goes through 1, and let's see what happens when we plug in e. What happens if I plug in e? What's the output? Is equal to 1, right? So this is e, 1. ln of e equals 1. Okay. Remember, they cancel each other. So that's the inverse of e to the x. Okay, and number 2, we have the common logarithm. And we define I should probably write this backwards. So let me write it the other way around. So ln of x is defined as log base e of x. And then we define log of x without writing anything as log base 10 of x. In math, typically, when you are defining something, when we write the equal sign, I'm defining something, then we put the 2 dots in here. These 2 dots means the definition of this is this. So these guys are equal by definition, not because they are equal for something. Like, for example, when you say 2 plus 3 equals x, and then you say x equals 5, we're not defining x to be 5. X is 5 because it's the result of doing 2 plus 3. Okay, so it's the result of something. Here, it's not the result of anything. It's just a notation that we're using. Okay, so that's why sometimes we express it this way. This means by definition, this thing is this. By definition, ln of x is log base. Okay. Okay, so we define log of x to be log base 10, and it's called common logarithm. For example, if you look at your calculator, most calculators, you only have 2 keys when it comes to log, ln and this one. Now, that, for example, mine only has log and ln. That's it. There are others that allows you, like when you can put like expressions that have a big screen, you can actually put the base and so on. And if you want to do log base 2 of 8, for example, you can actually type it. But in mine, you cannot do log base 2 of 8 directly. You need to use some properties that we're about to discuss soon. There's something called change of bases that allows you to change the base of a log and always write in base, for example, e or 10, and then you can compute. Okay? All right. Anyways, that's just some special notation. Okay. So I guess for completeness here, if you have the function f of x equals log of x, what's the graph of this? Is it a red or a blue graph? Is it a red or a blue graph?
Right.
It's a red graph because the base is 10. Right? So goes to 1, and then if I plug in 10, so I guess let me just, I'm not going to say that that's 10, so let's be a little bit more. Not be painful. But let's say 10 is somewhere in here. And this point here is 10,1. Okay? That is the red graph. But remember what I told you, this is a very slow growing function. Okay? All right. Questions? You okay with this? Okay, perfect. So I guess as a little example, let's sketch something and then let's find the domain of something. So let's see. Let's practice finding domain and sketching. So find the domain. And sketch. And let's do f of x equals ln of x plus 3. Okay, how do we find the domain of something like this? So let's find the domain without graphing first. So how do we find the domain? Remember, here you need to use the same logic that you do, for example, for square roots. When you find, if I tell you square root of x plus 3, what's the domain of this? So what question do you ask yourself? Say that again?
Make it equal to 0.
Why?
X plus 3.
Why?
Because then you subtract the 3 and it's actually equal to -3.
And what does that tell you? That tells me that that's 0. What's the problem with that? I'm asking for domain. Yeah, but there are infinitely many solutions. So what question do you ask yourself when you want to find the domain in something like this? Yes?
X plus 3 is greater than 0.
Why? Greater than or equal to?
Because it is going to be ln and it's going to be
No, let's focus on the square root. I'm asking about this now. So what question do you ask yourself?
if it's greater than 0 because it can't be 0 and it can't be negative.
What cannot be 0? I'm talking about the square root. Can you do square root of 0?
Inside of the 0.
It's okay to be 0. What's square root of 0?
No,
0.
0.
Okay. It's okay to do square root of 0. So what question do you ask yourself?
If it's equal, greater than or equal to 0.
Why do you ask that question?
Because it can't be negative.
Why?
It can be 0.
Because the square root, right? So in other words, so guys, you need to be able to extrapolate. Should I say this? There is a general thing that you ask yourself when you want to look for domain, right? It's not. It can be. You have to be greater than 0 because if you have a fraction, then the greater or less than 0 doesn't matter, right? But what's the question that you ask yourself when you're finding domain? What can go wrong? What's the problem with the expression that I have in front of me? Depending on the expression, there will be an answer to that. Okay? So for example, if you see this, what can go wrong? Well, the stuff inside here is negative. Because you know, square root of something negative is not good if you're only dealing with real numbers. So that's when you say, oh, then because I don't want this to be negative, therefore I need this to be greater than or equal to 0. Then you go that way. So in here, again, same question. What can go wrong? Then what operation are you doing? You're doing an ln of Okay, you have to think about it. When I do ln, what can go wrong? Well, I cannot do ln of negative stuff. I cannot even do ln of 0. As you remember, the domain is positive number from 0 to infinity. So you have to make sure that whatever is inside the ln is greater than 0. Do you understand what I'm saying? I'm telling you this because, in fact, we're going to do a couple more examples. And in fact, let's try something like this. Then I'm going to do something like this, plus 7. I'm going to put a square root. And I can start mixing stuff here. Then you have to have a more open mind if you want to answer questions like this. Okay? So keep that in mind. All right, anyways. So in here, what can go wrong is the fact that you cannot do ln of negative stuff, in fact, not even 0. So you have to make sure that the argument is positive. So if you want to find the domain, you need to make sure that whatever is inside the ln, it has to be positive. So this thing cannot be less than or equal to 0. Are you okay with this? All right. So in particular, then this tells me that x has to be bigger than negative 3. In other words, what's the domain? Draw a little picture. It is negative 3, not including negative 3, and everything to the right. So domain is negative 3 to infinity. Yes? Okay. So now let's graph it. How do we graph this function? What do we need to do? What do we do?
Take the standard ln function and shift to the left 3 units.
Very good. This is just transformation, right? This is the natural log function, and then we're shifting this to the left, horizontally to the left 3 units, right? So if we want to sketch this, we start with the parent function. Now to your list of basic functions, you need to add exponentials and logarithms, okay? Remember that we had that list of 8 basic functions from before. Now throw in exponential and log because, they are now part of the toolbox. So we start with ln, and then we do y equals ln of x plus 3. That's a valid transformation. Replace x by x plus 3. And what's happening from 1 to 2 is we are going left 3 units. Okay? So here's x, here's y. We have another log function. So we're going to use 1 and e comma 1 as our key points. Okay? And now we're going to move this. So now remember, in this case, there are several things that you need to move. In particular, we have a vertical asymptote that has to be moved also with the graph, depending what you're doing. For example, if you go up or down, if you do ln of x plus 3, will the vertical asymptote change? If you do a vertical shift, the vertical line, if you take a vertical line and you move it up, it's still the same line, right? So if you do a vertical shift, the line doesn't change, the vertical line. If you had a horizontal one, then yes, that one would change, okay? But vertical, no. And now if you do a horizontal shift, then the vertical line is going to change. Do you understand this? So now our line was, the original one is at x equals 0. Where does it go now? The vertical asymptote? X equals negative 3. So 1, 2, 3. So now we're going to have a vertical asymptote here. It went from 0 to negative 3. And now let's move our point. So the point 1, 0 is going to go to negative 2. And then the point e comma 1 is gonna go to e minus 3. Remember, e is 2 point something, so this is 2 point something minus 3 is negative 0 point something. Okay? So it's gonna be somewhere in here. Let's say this guy here is e minus 3, comma 1. And now we graph. Okay. Remember, every time that intercepts show up, we need to find them, and now we have the knowledge to find them. So who is this guy? And what is it? What is this? ln of 3. If you want to know what that is, well, use your calculator, and you get about 1.098, whatever. Okay? But the exact value is ln of 3. Just like if you say square root of 3 is square root of 5. Okay? This is ln of 3. All right. Questions? Do you understand this? Okay. So that was that. And again, now for example, you can take this off, and you can combine this with a bunch of other transformations. In the homework, you will do this kind of stuff. So let us keep finding domain. So domain, let's find the domain. And let's see, let's do y equals ln of x squared minus 1. And then I guess let's do square root of log base 2 of x minus 7 plus 3. I don't know. Let's do something like this. Just to practice. Okay, so try part A. Let me take attendance as you do so. Antoine Tela.
Here.
Gabriela Rue.
Here.
Isabela Bagaya.
Here.
Anabel Bamori. Kevin Bonson.
Here.
Wyatt Boynton.
Here.
Ariel Busutil.
Here.
Samantha Cabrera.
Here.
Juan Camacho. César Castañeda. Natalie Castañeda. Mary de la Cruz. David Fajardo. Lexi Galvez. Maximilian George. Saint Gettinger.
Here.
Raúl Izquierdo.
Here.
Farzana Khan. Gabriel Culi.
Here.
Bernardo López. Natalie Martínez. Dayani Plasencia. Arisai Rodríguez. José Rodríguez. San Rodríguez. Sara Sacrani. Lucas Sam. Lucía Sánchez. María Sánchez. John Paul Sánchez. Shane Soto. Deandre Toledo.
Here.
Gabriel Trompeter. Genesis Trujillo. Héctor Vega. Christopher von der Haar. Alexander Warner. Okay. All right. So what can we say about part A? What's the domain in this case? Okay. So you're saying that 1/2, you're saying that 0, for example, is okay. Because -1 to 1 is in the interval, 0 is in the interval -1 to 1. Are you saying that 0 is okay?
Yeah.
What happens if you plug in 0? What do you get?
No.
And what's ln of -1?
So, not
So again, I tried to tell you that earlier. It's not about solving an equation. It's not an equation where you need to solve. You just solve the equation square minus 1 equals 0. But that's not what you need to do. It's not an equation where you need to solve. Yes.
You need to do x squared minus 1 greater than 0.
Very good. You need to solve an inequality. Again, you're doing an ln. What can go wrong? That the stuff inside is negative or 0, right? So you need to impose that the stuff inside is greater than 0. Yes?
it's 1,30.
So you are saying that -2 is not good?
No.
What happens if I plug in -2?
Yeah, -3.
So have to be careful. So again, what can go wrong here if we're finding the domain is that the stuff inside can be less than or equal than 0. So let's make sure that that doesn't happen. In other words, we need x squared minus 1 greater than 0. So now the question is, how do we solve this? You just had an exam that you have to deal with this. How do we do polynomial inequalities? This is a polynomial now. How do we do polynomial inequalities? No.
You simplify it, you factor it, or
So you find the zeros, which you factor so that you can get the 0 easily. You find the zeros, and then what do you do?
Find the intervals where it's positive and negative.
You put them in a line, and then you start testing to see when it's positive, when it's negative, and then you decide what you want, the plus or the minus. Do you already forgot this? We just did an exam on this last time on Thursday. It is a polynomial inequality. So x plus 1, x minus 1, and we factor because it's easier to find the zeros. So the zeros are -1 and 1. I don't want them because it's greater than 0, so we do open circle. And now we just find the sign. So when you find the sign in each piece, you're going to get positive, negative, positive. Right? By picking a point, plugging in, or in this case, you can use the end behavior together with the fact that the multiplicities are 1, so you cross every time. Okay? However you want. The point is that you figured out the sign, and then what do we want? Plus or minus? What do we want? We want the plus because it says greater than 0. So we want this, and we want this. So what is the domain? So the domain is negative infinity to -1, union 1 to infinity. Is that clear? Okay. So now let's do the next one. So we have y equals square root of log base 2 of x minus 7 plus 3. All right, so what do we need to ask ourselves to find the domain of this function?
well, there's two things. There's the square root, you need to put everything that's under the square root greater than or equal to 0, and then also everything x minus 7 greater than 3.
So let's take this to the very top level. So what's the question? What can go wrong? Or what can go wrong here? Look at the expression. When you see a square root, first thing that can go wrong is that the stuff inside is negative. And it could be, remember, the range of this is negative infinity to positive infinity. So you can have here a -5, for example. And then when you do +3, you already throw, right? So there are some restrictions that we need to make. So the square root, what can go wrong is that the square root, the stuff inside could be negative. We need to take care of that. Now, that's not the only thing that we have to take care of. Also, inside the square root, when we look at it, we see a log. And when you see a log, the stuff inside the log in the argument cannot be less than or equal than 0. So that could also be wrong. For example, 1 is not a good value to plug in here. If you plug in 1, this is an issue. Do you understand this? So, two things that your classmate pointed out. So, first thing is that we need to ensure that the stuff inside is greater than or equal than 0, right? And then we also have to make sure that the stuff inside the logarithmic itself is strictly greater than 0. Do you understand this? Once we take care of this, is there anything else that we should concern ourselves with? No, right? All right, so let's see. This one is easy. So this right here, by the way, what we're going to do is, once you have 1 and 2, we're going to do the intersection of the two. Because we need to make sure that whatever our x is, it's okay for number 2 and it's also okay for number 1. Okay? So we're just going to take the intersection of the two. Okay, so number 2 tells me that x has to be bigger than 7. All right, now let's see what number 1 is telling us. So now here, this is actually a logarithmic inequality. But we can do this and then explain you how to do this systematically, and this will nicely introduce for equations later. So I'm just going to move the 3 to the other side, okay? Now here I have a statement that log base 2 of x minus 7 is greater than or equal than 3, okay? Now I want to have access to x, so I can solve for x. So to be able to have access to x, I first need to get rid of the log. For example, if you have this equation, this statement, what do you do to get access to x? What would you do to get access to x? Why are you raising to the power 2? To get rid of the square root. What's raising to the power 2 does to this? So what does the power raising to the power 2 have to do with the square root? What are they? They are inverse of each other, with the restriction of the square and so on, right? So they are inverse of each other. They cancel each other. So similarly, if to get access to x, you need to cancel this function. So to get access to this term here that has an x, I need to cancel this function. What cancels this function? The inverse, right? What's the inverse of this function? What's the inverse of log base 2? We just define it. What is it? What's the inverse of log base 2? 2 to the x. I mean, aren't we saying this for 1 hour already? So if you want to get access to this guy, you need to get rid of the log. How do you get rid of the log? Well, raise it to the power 2 to this power is going to cancel this log, right? That's the inverse function. So that's what I'm going to do, okay? So that's the same thing when you have square root, you square both sides to get rid of the square root. Okay, if you have a log, then you need to exponentiate if you want to get rid of the log, okay? Also the other way around, if you have an exponential, you need to do log if you want to get rid of the exponential. This is the idea that you use to solve equations, logarithmic and exponential equations. Okay, so what I'm going to do is I'm going to raise to the power of 2, okay? So I'm going to do 2 raised to this. And then, of course, if you do it on one side, you need to do it on the other. Now comes the other question. What do I do with this guy? Does it stay the same or does it flip? So does it stay the same or does it flip? So this has to do with the function 2 to the x itself. What do we know about the function 2 to the x? Let me, I don't want to write the whole thing again, so let me just bring it here. So what do we know about the function 2 to the x? It's a red graph, right? So in particular, what do we know about this? This is an increasing function, right? So what does it mean to be increasing? So increasing means, graphically it means that the picture is going up, but it also means that whenever you give it 2 inputs, if x1 is less than x2, then y1 is going to be less than y2. In other words, as you move, what does it mean to go up? As you go from left to right, so as you go from smaller to bigger in the x-axis, you go from bottom to top on the y. Right? If you increase the input, then you also increase the output. That's what increasing means. Decreasing is the opposite. If you increase the input, you decrease the output. Okay? So let's see what this means in terms of inequality. So if x1 is less than or equal than x2, what do you think happens to 2 to the x1 versus 2 to the x2? Let's see. This guy is bigger than this one, so if I do 2 to this power, what am I going to get? Something bigger, because if the input is bigger, then the output is going to be bigger. Yes? Because it's increasing. So that means that doing 2 to some power, in fact, b to the x, where b is bigger than 1, respects inequality. Doesn't change. And just since we're here, I should have done this right. Now, let's do the blue version. So let's do 1/2. So instead of this, I'm going to do 1/2 to the x minus 1. No, for some reason, maybe you're dealing with log base 1/2, for example, and then you need to do 1/2. Instead of 2 to the power, you do 1/2 to the power. What happens now? Because 1/2 to the x is a decreasing function, what does that mean? The bigger the input, the smaller the output, because your graph is going down. You understand this? So what's going to happen to the inequality here? It's going to flip, because x2 is bigger, therefore this number now is smaller. Do you understand this? So whenever you want to figure out whether, when you do an operation, if the inequality is preserved or not, meaning, if you should keep it the way it is, or if you should flip it, you need to ask yourself, okay, the operation that I'm doing as a function, what is it? Is it an increasing or a decreasing function? If it's increasing, you keep it as it is. If it's decreasing, you have to flip. Okay? For example, what's now that we have this point of view? What's the rule when you're solving inequalities? What happens when you multiply by a negative? Why? Okay, but now from this point of view, why? What does it mean to multiply by -1? What function corresponds to that operation? Okay, and how does y equals -x looks like? It's a decreasing function, right? Here is your y equals -x. Right? It's a decreasing function, therefore, if you apply this function to an inequality, you have to flip the sign. Now you see a formula, the reason why this happens. Okay? All right. Okay, so let's continue. By the way, what we're doing here is something that's a little bit outside what we normally do in this course, because here we're solving a logarithmic inequality. We typically just do logarithmic equations, but you know, there's really no reason why we cannot do a logarithmic inequality, because there is not much involved. Okay, it's just understanding this relationship of increasing, decreasing, and how the inequality behaves. Other than that, you solve it like an equation. Okay, so I want to get rid of this guy, so I apply 2 to the power of this, because the 2 counts as the log base 2, but then because 2 to the x is increasing, that means that the inequality stays as it is. Okay? All right, and well, now we are in business, because the 2 counts as the log base 2, so what is this, the left-hand side? What do we get in the left-hand side? X minus 7. Greater than or equal than 1 over 8, right? Therefore, x has to be greater than or equal than 7 plus 1 over 8, which is 7 and 1 8, and then what is this? 56, 57, right? 57 over 8. It's nice to say it like this because notice that this is slightly bigger than that guy. Okay? So when we put the 2 statements together, here we have 7. Here we have, well, it's actually very, very close, but let me keep it like this. 57 over 8. This is 7 and 1 8. And then I don't want this guy. This one is okay because it says they're now equal to, so that one is okay. And then this is like this. This one is like this. And because we want the intersection, we want to make sure that we are okay for both expressions. Hopefully you can see that the common region is this. Yes?
Could you have changed it from the moment it was just log base 2x minus 7 is greater than or equal to -3 to 2 to the -3rd is greater than or equal to x minus 7?
Yeah, exactly. But then what do you do with the inequality? So how do you know whether you have to keep it the same or not? You see, because what if it was base 1/2? Are you going to keep it the same? You can do that, but then is it the same? So that's why I went this approach to justify why I have to keep it like this. Okay? Because actually, let's see, repeat the same thing that you said.
Change the log base 2x minus 7 is greater than or equal to -3 to 2 to the -3rd is greater than or equal to x minus 7.
You see, you just said it wrong. It will be is less than. Look at this statement. Because now this guy goes over here. So it will be 2 to the -3 is less than x minus 7. You see? You have to be careful. So to avoid confusion, it's better to, it's more clear if we do this. But yeah, you can do that as long as you understand where the symbol goes. Okay. Anyways, the point is that now we have the domain, which is bracket 57 over 8, comma infinity.